Hello, I'm Differential working as Assistant Professor in the Department of ECE SJBIT. In this video, I'll be discussing about the line codes. So, previously we have discussed about the PCM. So in PCM, in the last video, we have discussed about the sampler, quantizer and encoder, and in the encoder the next step is the line codes, that is different ways of representing the data. So that will be discussed in today's video. So it is a line code that a binary stream of data takes on an electrical representation. Any one of several line codes can be used for the electrical representation of a binary data stream. So here in this diagram, we can see the waveforms of 5 important line codes for the data 0, 1, 1, 0, 1, 0, 0, 1. So the line codes often used the terminology that is non-return to 0, NRZ, non-return to 0, and return to 0, RZ. So return to 0 implies that the pulse shape used to represent the bit always return to 0 volts or the neutral level before the end of the bit. Non-return to 0 indicates that the pulse do not necessarily return to the neutral level before the end of the bit. So we'll take up one by one. The first one is unipolar non-return to 0 sampling. So here in this line code, symbol 1 is represented by transmitting a pulse of amplitude A for certain duration of the symbol, and symbol 0, it is represented as switching off the pulse. So 0 is like 0 itself. So as you can see in this here, 0 is taken as 0 itself, 1 is represented with the amplitude A, 1 with amplitude A, 0 with 0, 1 that is equal to amplitude A, and it goes on like this. This line code is also referred to as on-off signaling. So the disadvantage of on-off signaling is the waste of power due to the transmitted DC level. This is about unipolar non-return to 0 signaling. Next is polar non-return to 0 signaling. So here in this, symbol 1 and 0 are represented by transmitting the pulse of amplitudes plus A, 0 as minus A respectively. So observe here, 0 is represented as minus A, 1 is represented as plus A, 1 plus A, 0 minus A, 1 plus A, 0 minus A, 0 minus A, 1 plus A, like this it goes on. This code line, it is relatively easy to generate and it is more power efficient than the previous unipolar non-return to 0 signal. The next one is unipolar return to 0. So here in this line code, symbol 1 here, this is unipolar return to 0. Symbol 1 is represented as a pulse of amplitude A and half symbol width. half symbol width with amplitude A, and symbol 0 is represented as no pulse, 0 itself. So you can observe here 0 is taken as 0 itself, 1 is taken as positive plus A for half of the symbol and 0 for the negative half the symbol. Means 1 is represented as like this and 0 is 0. So an attractive feature of this line code is the presence of the delta function at f is equal to 0 plus or minus 1 by dB in the power spectrum of the transmitted signal, which can be used for bit timing recovery of the receiver. However, its disadvantage is that it requires 3 dB more power than polar return to 0 signaling for the same probability of symbol error. Next type is this one. It is bipolar return to 0 signaling. So this line code uses 3 amplitude levels. Positive and negative pulses of equal amplitude, that is plus A and minus A, which will be used alternatively for symbol A. With each pulse, when 0 is represented as no pulse, means for the first occurring one, it will be having plus neutral. For the next one, it will be in the reverse direction, minus A neutral. For the next occurring one, wherever is it, after a series of zeros and all, wherever it is occurring, it will be like plus A and neutral. So you can observe here 0 is taken as 0 itself. This one is represented as, it is divided into two halves. First half plus A and then 0. Next one is taken as minus A, 0. Next we have 0, so it is taken as 0. So next we have 1. So what is the previously transmitted one? It is minus A and 0. So the next one will be plus A and 0. Next we have 0, 0 as it is. Next we have 1. So previously transmitted one is plus A and 0. So now 1 is taken as minus A and 0. So like this the values will be transmitted. A useful property of this bipolar return to 0 signaling is that the power spectrum of the transmitted signal has no DC component and relatively insignificant low frequency components for the case when symbols 1 and 0 occur with equal probability. This line code, it is also referred to as AMI, that is alternate mark inversion signaling. Alternate mark inversion signaling. Next, Manchester coding, or you can also call this as Manchester coding, or you can also call this as split phase. So in this method of signaling, symbol 1 is represented as positive pulse of A followed by a negative pulse of E, plus A, minus A, like this, with both the pulses being half symbol wide. 0 is represented as 2 pulses and are reversed. So the Manchester coding, it looks like this. You have a 0, so it is minus A plus A. Then you have one plus A minus A. Then you have one plus A minus A. Then you have 0 minus A plus A. 1 plus A minus A. Like this it goes on. So the Manchester code, it suppresses the DC component and has relatively insignificant low frequency components regardless of the signal statistics. This property is essential in some applications. So these are all the different 5 signaling methods. Next you have differential encoding. So here in this method, it is used to encode the information in terms of signal transitions in order to signal transitions. Transition, it is used to designate a symbol 0 in the incoming stream, while there is no transition to describe symbol 1. Means whenever there is a transition from 0 to 1, there is no changes. Whenever there is a transition from 1 to 0, there is a difference. Observe here. So whenever the next appearing symbol is 0, this is the original data, this is the differentially obtained data. When the next appearing data is 0, the value will be 0. Next is 1, so there is no change. 1, no change. When there is our next appearing data to be 0, there is a shift from 0 to 1. Next 1, 0. So next appearing data is 0. So whatever is the previous state, it gets inverted. So next appearing is 0. So whatever is the previous state, next get inverted. So like this it happens. The original data stream used here is the same as that we have used for this example. If you have observed, the waveforms of the differentially encoded coding is somewhat like this, assuming the use of unipolar non-return to 0 signaling. So it is apparent that a differentially encoded signal may be inverted without affecting its interpretation. The original binary information is recovered simply by comparing the polarity of adjacent binary symbols to establish whether or not a transition has occurred or not. Note that differential encoding requires the use of reference bit before initiating the encoding process. So this is about the differential encoding. Next is the regeneration. So the most important feature of any digital system, it is in the ability to control the effects of distortion and noise produced by transmitting a digital signal through a channel. This capability, it is accomplished by reconstructing the signal by means of a chain of regenerative repeaters. It happens to be in the channel, which is located at sufficiently close spacing along the route. So 3 basic functions are performed by the regenerative repeaters. One is the equalizer, another one is the timing circuit, another one is the decision making circuit. The equalizer shapes the received pulses so as to compensate for the effect of amplitude and phase distortion produced by the transmission characteristics of the channel. The timing circuitry here, this provides a periodic pulse train which is derived from the received pulses for sampling the equalized pulses at the instance of time where the signal to noise ratio is a maximum. The sample so extracted is compared to a predetermined threshold in the decision making device. In each bit interval, a decision is then made whether the symbol is 1 or 0 on the basis of whether the threshold is exceeded or not. If the threshold is exceeded, a clean new pulse representing symbol 1 is transmitted to the next repeater. Otherwise, a clean 0 pulse is transmitted. So, in this way, the accumulation of distortion and noise in a repeater span is completely removed, provided that the disturbance is too large to cause an error in the decision making process. Except for the delay, the regenerated signal is exactly the same as the signal originally transmitted. However, the regenerated signal, it departs from the original signal mainly because of these two reasons. One is the unavoidable presence of channel noise and interference causes the repeater to make wrong decisions occasionally, thereby introducing bit errors into the regenerated signal. Second point is, if the spacing between two pulses deviates from its assigned value, a jitter is introduced into the regenerated pulse position, thereby causing the distortion. Then, the decoding. This is the last part in the PCM. That is, in the decoding, we have decoding and the filtering. So, the first operation in the receiver, it is to regenerate. Regenerate means it is reshaping and cleaning up the received pulses one last time. These clean pulses are then will be regrouped into code words and decoded into a quantized PAM signal. The decoding process, it involves generating a pulse, the amplitude of which it is a linear sum of all the pulses in the code word, with each pulse being weighed by its place value, say for example 2 power 0, 2 power 1, 2 power 2 till 2 power r minus 1. So, in the code where r is the number of bits per sample. The last part is the filtering part. The final operation in the receiver, it is to recover the message signal wave by passing the decoder output through a low reconstruction filter whose cutoff frequency is equal to the message bandwidth W. Assuming that the transmission path is error free, the recovered signal, it includes no noise with the exception of the initial distortion introduced by the quantization process. The last topic is the multiplexing. In multiplexing, in the applications using PCM, it is natural to multiplex different message sources by time division, whereby each source keeps it individually throughout the journey from the transmitter to the receiver. So, this individuality accounts for the comparative ease with which message sources may be dropped or reinserted in a time division multiplex system. As the number of independent message sources is increased, the time interval that may be allotted to each source has to be reduced, since all of them must be accommodated into a time interval equal to the reciprocal of the sampling time. Thus, in turn, it means that the allowable duration of a code word representing a single sample, it is reduced. However, pulses tend to become more difficult to generate and to transmit as their duration is reduced. If the pulses become too short, impairments in the transmission medium begin to interfere with the proper operation of the system. Accordingly, in practice, it is necessary to restrict the number of independent message sources that can be included with the time division group. So, this is all about the PCM generation at the transmitter side, how it will be operating at the channel, and how is this going to operate at the receiver side. In the next video will be discussing about the delta modulation. Thank you.